Welcome to H Squared, it's officially understood science. Today we're going to be taking a look at the periodic table of elements. I am Mr. Holsey, I'll be your guide today. So the periodic table of elements was created by my beard brother Dmitry Mendeleev, and he was the first scientist to really notice the relationship between the elements. Now at this time there were a lot of people trying to develop a periodic table. Now the story is that Dmitry actually came up with his idea during a dream. He'd been working on it for a long time and he came up with this during a dream. So it's kind of a wild story, and his story is insane, how he came to becoming such a respected scientist. Now, he arranged his periodic table by atomic mass and said that properties of unknown elements could be predicted by the properties of elements around the missing element. So he was fairly accurate in all this, so much so that when a French scientist claimed to have discovered a new element, Dmitry actually wrote papers saying how that scientist was wrong, even though he'd never seen this element. And Dmitry was right, because Dmitry Mendeleev was crazy smart. So Mendeleev's table looked a lot different than what we would know as the periodic table today, but you still see a lot of the same things. Like you can see hydrogen right there, lithium down below it. And so you can see a lot of the same elements are already there, but they're put there by their atomic mass. If you remember, atomic mass is the weight of the nucleus. So another big pioneer was Moseley, who later discovered that the periodic nature of the element was not associated with the atomic number, it was associated with the atomic number and not the atomic mass. Now, the reason why is that the atomic mass is the protons and the neutrons. Sometimes you'll have more neutrons than you have protons. That just kind of happens. But the protons, which is equal to the atomic number, is what determines the identity of an element. And so you can see how Moseley made his periodic table right there. Very similar to what we see today. Now you notice there aren't a lot of as many elements as what we have, but they are working. They were working on that. So the periodic table is broken up into columns or groups. And we sometimes call these columns families. And so like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So there are 18 columns on the periodic table. Okay? And so they run up and down. Now the periodic table is also made up of rows or periods, and there are 7 rows on the periodic table. So we have 1, 2, 3, 4, 5, 6, 7. Now you're probably wondering, well, what about these guys right here? Okay, so these actually fit in right there. Those actually fit in right there. So let's talk about the significance of the periods on the periodic table. And once again, we're talking about these horizontal rows. So periods are the name of the rows of the periodic table. Now all elements in a period have the same number of electron shells. So if we are in period 1, all elements in here have 1 electron shell. If we are on period 2, they have 2 electron shells. All of these elements have 2 electron shells. And if we're in period 3, same deal. And this is really important when developing atomic structure, because if you know the number of electron shells, you have a good idea of what the electron configuration is going to be. Now let's talk about the groups. So the groups are going to be these vertical columns, and they're going to go 1 through 17. Now we're not going to focus too much on these. These are the transition metals this year, so we're not going to focus too much on the transition metals when it comes to Bohr models, but we're going to talk about their characteristics. So the organization of the periodic tables, their groups and families. Think about you. I mean, you have a family, right? And so families tend to have similar characteristics, whether it be mannerisms or if it is something as simple as looks. And so these are elements that are in the same group or family tend to have similar characteristics to one another. That's why they're in the groups. And this is the name for the columns in the periodic table. Now, if we take a look at this, so all elements in a group have the same number of valence electrons in their outer shell. And so if we are in group 1, okay, it has 1 valence electron. But what if we are in group 17? Will we have 17 valence electrons? No, you would have 7 valence electrons. Essentially, you're going to mark it out, because sometimes if you're in group 17, you'll see it written as group 7A, or so on and so forth. So it means that's 7 valence electrons. So let's talk about these different groups in the periodic table. So first up, we have the alkali metals, which is group 1. Now, hydrogen is not considered an alkali metal because it's not a metal, but it is grouped with group 1. The reason for that is it does show characteristics of alkali metal, and with group 7, the halogens, which you could argue it could be placed in either, especially the halogens because it's a non-metal. However, the reactivity of it, because of its 1 valence electron, and for grouping purposes, they typically put it above these alkali metals, but it is not one of them. So it has 1 electron in the outer shell, has 1 electron in the outermost shell, and they tend to be soft and silvery metals. So all these are metals. All these right there are metals. So they are very reactive, very, very reactive, especially when they come into contact with water, and they do conduct electricity. So these, if you ever take a moment, look up sodium in water. What happens when you put pure sodium in water? It's absolutely awesome, because basically what it does is it goes boom, like big booms. And so look up sodium in water. It's actually worth a little bit of a watch. So group 2 is the alkaline earth metals, and those have 2 electrons in the outer shell. These tend to be white and malleable, which means that they can be molded. They are very reactive, but less reactive than the alkali metals. When it comes to the metals, the further you get over this way to the right, the less reactive they become. And they do conduct electricity as well. The transition metals are right here in the center. Now, we're not going to spend too much time talking about those this year, other than their groups. As far as we're going to talk about them outside of talking about Bohr models. So these are good conductors of heat and electricity. Some of these are going to be used for jewelry, like gold, copper, silver. They can bond with many elements in a variety of shapes. They call them the transition metals because they're transitioning in this direction, becoming less and less metally, if that makes sense. They're transitioning to the non-metal side. So we're going to skip these groups right here because they're not that important. But I will tell you, so this group right here, this is the boron group, this is the carbon group, the nitrogen group, the oxygen group. They're pretty much mostly non-metals, except right here we have some metalloids that we'll deal with at a different time. But they're just basically there. They're just elements, but they don't have any big significance to what we're going to be talking about. So halogens, or group 7, they have 7 electrons in the outer shell. Now, these are also known as group 17 sometimes because it has a 17 over it, because it is, group 17. But we also refer to it as group 7 because what we'll do is we'll name this like 1A, 2A, 3A, so on and so forth. And this will be in the B's. This will be like 3B and stuff like that. So don't worry about that just right now. So we're going to call this group 7 though, because it has 7 valence electrons in the outermost shell. Now, if you remember, I said things tend to become less and less reactive as you move over. That's for the metals. Okay. For the non-metals, it's kind of the opposite. If you're moving from right to left, you're becoming more reactive, and that's where that little metalloid line really comes into play, because we're transitioning from metals to non-metals. And so the metalloids are kind of like this in between metal and non-metal. And so group 7, they are going to be really interesting because they are all non-metals, but they are extremely reactive. So as you're going along with the metals, you're becoming less reactive as you go along. As you're moving, you become less reactive with the metals. And then over here, though, as you move from right to left, the non-metals become more reactive. It's actually the opposite, because the reason is these have 7 valence electrons, and so these halogens are looking just to have one more valence electron to kind of fill them out. They're looking for one more valence electron, and so they're going to react with whatever they can. And so these halogens are going to be very, very reactive. This is also sometimes called like the salt group, because they will bond really, really well with sodium, like sodium chloride, which is table salt. And so they will bond with sodium pretty well. And then over here you have the noble gases, group 8 or group 18. And so these exist as gases. They are all non-metals. They have 8 electrons in the outer shell, which means they are full. These are also known as inert gases, meaning they do not react with other elements. Okay, they are just it. Now, helium's a little bit of a different story as far as its electron shells, because it is in period 1. The first electron shell can only hold 2 electrons. And so helium is full because it has its 2 electrons. But the rest will have 8. So these are, like I said, not reactive at all with other elements. Then we have the rare earth metals, which are the special rows on the bottom of the periodic table. You have the anthonides and the lanthanides. And some of these are radioactive. Some of them only exist for a short period of time. The rare earth metals are silvery, silver white, or gray metals that conduct electricity. They're more similar to one another. It's harder to tell these apart. So I hope you've enjoyed today's lesson. Hit the like button, share, subscribe, hit the bell icon because YouTube doesn't know how to work at all. And we'll catch you later here on Sufficiently Understood Science.